I'm Xianying Zhang from PerfXLab. I will give a talk about PerfXLM, a high-performance large language model inference engine on RISC-V CPUs. Firstly, I will introduce our team briefly. PerfXLab technology founded in 2016, and we provided a heterogeneous computing software stack for the CPU and the GPU vendor, for NPU vendor, and also for the computing data center, and also for the application, including AI algorithm, AI info, and other like EDA software. And the Profress API is our core product, which includes the performance level, the different library for RISC-V CPUs, for the OpenCL CPUs. We also have the CUDA version. And on the framework level, we have the heterogeneous the scheduler, and also have the API, and also have the AI inference and tools. And this talk focuses on our large language AI inference, PerfXLM. PerfXLM also have the 3 levels. The top level is about the model, how to present, how to describe the large language model. We convert, for example, the Llama model into Onyx graph, and to run the graph fusion and other optimization. And the next level is engine level. The engine level to control the memory alloc to serving the language inference, and also have the to call the bottom kernel to the different kernel optimized for the different device, for example, for the RISC-V, for the CUDA device. And we check the detail on the first interface level. We want the user can use our inference smoothly, so we have the compatible API with the VLLM. So if the user can just change the Python code, one line Python code to our PerfXLM, they can run the large language model inference. And in the model, how to describe the model, we use the Python code and the torch style to describe the Llama or other language model. And the next step, we create the graph based on the Onyx OP, and in that graph we apply the OP fusion, the graph fusion optimization to the model. So for the Llama model, there are only 7 fields OP in this graph left in the final fusion. So this is good news for the NPU or for the ASIC vendor, because the NPU only need to support a fewer OP compared to the CNN model. And the next step, the engine level called the graph in the array OP into the different layer, to the different library implementation. So in the optimization methods, we use the low precision quantization, like quantization of the weight, AWQ int 4, and the feature map is the floating point 16. We also support the quantization for KV cache, and for the embedded system, we suggest use the int 4 precision, because they cost less memory. Here, a smaller memory port. But for the server side, on the data center side, we suggest use the floating point 8 or integer 8 precision, because the model performance is the precision of the model is very important on the server, and also has the operation fusion, the fields of the and the base and the layer mode, the fields of the QKV, GEMM, and also other the core kernel optimization. For example, for the matrix multiplication, space is must to take care of the Tor and the ski matrix is very important for the pre-fail stage in the large language model. So we also porting the PerfXLM on RISC-V. The testbed is the SG2062, and the IRE core supports the RVV 0.7 and have the L1DS 64 gigabytes, and the 4 cores the IRE cluster have the 4 cores, and the chip have the 16 cluster. So the total have in total the chip has the 16 cores, and the chip has the 4 DDR4 memory controller. And here is our performance result of the GEMM optimization for the pre-fill stage. And this graph shows the performance for the big and the square matrices is the general matrix multiplication. But for the large language models, especially for the single batch user scenario, the matrix is a tall and a skinny matrix. So this graph shows the tall and the skinny matrix performance. And you can see here is a big different performance. For example, for the large matrix, we can achieve 210 GOPS. But for the tall and skinny matrix, it's only less than the 90 GOPS, so only have half of the large matrices. So here is the bottleneck for the performance stage. Also, we can see the int4 GEMM doesn't mean we compute the matrix in the integer fully. We just dequantization the weight from the int4 to the floating point 16, and the computing is in the floating point 16. So if you design the matrix instruction extension, so the floating point is very important. So, and the next kernel is the GEMV optimization for the decoding stage, and the decoding stage is a memory bandwidth kernel. So we test the difference. We test the performance depends on the different threads. We test the performance on the 32 threads. We also test the performance on the 64 threads. We use the thread affinity or no affinity. So the red line is the red one line, and the best performance is 32 threads with the affinity, which indicates in that chip the memory, the 4 memory controller is not enough for the 64 cores. So we need more memory controller. So for the 64 cores, so have the slower than the 32 threads. So, and we put them on. We achieved we can run the Llama 2 7B model on the RISC-V CPU natively. We used the quantization AWQ-int4, and the decoding speed is 4.0 tokens per second. It's 10 times and to the 50 times speed up compared to the Llama.cpp native implementation, and the first token latency is 6 seconds. The memory footprint is 3.7 gigabytes, and in our implementation, we used the 32 thread, not the 64 thread. And here, this graph shows some the output result on our Llama on the RISC-V. You can see show some introduce what is Open Blast. It's our open source project. So also here is some performance graph on different architecture. For example, on the GPU, we have the better performance compared to the LLM on the Llama 3. The summary is the PerfXLM is a large language model inference engine. We have the compatible API. We support the RISC-V and other embedded GPU or storage GPU, and we have the better performance. But for the RISC-V, we suggest we must the CPU vendor must integrate more memory controller or the higher bandwidth memory into the CPU, for example, the HBM. So if we can achieve the AI PC of the RISC-V version. So in my opinion, the AI PC must have the 10 tokens per second. So far, we only have 4 tokens per second. So that's all. Thank you.
Thank you, Shanyi. Any questions for Shanyi and his presentation? And the previous slide, 2 back, you were talking about performance compared to NVIDIA.
Okay.
Yeah, you went through that slide sort of quick. I just wanted to stare at it. Maybe other people wanted to stare at it a bit, because it seems like there's some good data there about RISC-V versus the NVIDIA GPUs.
Yeah, because our inference engine, not just for the RISC-V, we support a lot of devices. So we have to optimize for the RISC-V CPU, optimize for the NVIDIA GPU or other China homegrown GPU. Okay.
Okay, very good.
Thank you.